And I'm going to get to the whiteboard. Okay, so I hope you all have a nice break. And now, what I want to do today is I'm going to do most of this on the whiteboard. So as I'm doing it, guys, copy it down in your notes because I'm going to do it once. And what I want to show you is how to design that connection for the drop-in beam or the link beam in the Gerber system. Now, if you remember, we have, for example, we have a beam here, I should say a girder here. And then, like, this is going to be supported on a column here. And then we had another beam in here. This is the drop-in beam. And then here we had the other one that had a double cantilever. So this is basically, so this is, okay. So what we want to do is we want to provide some kind of connection in here. So the way that I see this being done is so the nicest thing to do here is that this girder here will get installed, and then this girder here will get installed. So basically what you want to do is you want to be able to weld some kind of a plate in here. Just a weld. And then what you're going to do is you're going to have holes in here, and we'll determine how many we need and all that. And therefore, when this gets installed, they'll be able to put this right next to it. And then, of course, the holes in the beams, that's all going to get detailed by the people that are fabricating and erecting the structure. And then after that, they'll be able to simply connect the two together. So in order to design this, what we need to do is we need to know what's the force that is going to be transmitted from this beam to this beam. And I went to ADA, and I know that the VF force here, the highest VF force of all the cases that we analyzed was 333 kilonewtons. Now, it could be 333, 35, that's the ballpark, okay? So we have to design for a force of at least 333 kilonewtons in order to make sure that this beam can adequately be supported and that this whole connection here has the whole mechanism to go from one side to the other. So the first thing we do is we try to determine how many bolts are we going to need in order for these two elements, in other words, the beam and the plate to be, how many bolts will we need so we connect the beam to the plate. So we know that we have a VF force of 333 kilonewtons. And then if we assume that we're going to be using 3/4 inch diameter A325 bolts, and if we assume that the threads are going to be intercepted, then the VR for this, if you go to the table, the VR for this is 79 kilonewtons, and that's what the threads interact per bolt. So if we want to determine, so therefore, if we have 79 kilonewtons per bolt, and N is the number of bolts, is equal to, should be greater than or equal to 330 kilonewtons, 233 kilonewtons, so N is going to be 333 kilonewtons divided by 79. And if somebody did the math with me, but I did this and I got like about 4.2 volts.
Sir?
Yeah.
I don't think I really, can you like tell the numbers again, because I can't really read what you just wrote.
Well, it's because like as I'm writing it, you should be writing it down also, because
I know I am writing it, but like I don't really.
Okay, so in other words, this is my VF force that's
right.
being at the end of the beam. That's the highest one, 333 kilonewtons. we're going to be using 3/4 inch A325 bolts.
Okay.
The VR, if you assume that the threads are going to be intercepted, because you're not sure, the VR is 79 kilonewtons per bolt. Okay? So therefore, if I want to determine how many bolts I need, I take 333 kilonewtons divided by 79 kilonewtons per bolt, and I end up getting 4.2 bolts. So I'm going to use at least 5 bolts. So I'm going to have here a 5-bolt configuration.
Right.
Okay. Now, what I'm going to do is I'm going to erase some of this stuff. So I'm going to erase all of this. So now the next step is working out some kind of plate size. Okay. So I'm going to try to draw this. Sorry?
So there's 5 bolts on the plate holding it?
Well, we're going to be putting 5 bolts to attach this beam or this girder to this plate. Now, I'm going to try to draw this. What color should we draw it in? Let's draw it in.
Sir?
Yes.
Is that going to be the same for either side of the
Oh, yeah,
dropping beam?
yeah. In other words, whatever I design for this side will apply to this side, because I think the VF on this side is just slightly higher than the VF on that side. So I want to get the VF right across the whole thing, right? I took the highest VF value of 333. So whatever I'm designing here is going to be the mirror image on this side, and then whatever is going to be doing here, we'll be doing it on the other end, the other side of the girder. It's all going to be the same.
Thank you.
Okay. So now, I'm going to try to draw this so that we can, because this, we're going to have to refer to this quite a bit. So I'm going to try to draw this. Okay. So this here, I should have made this a little bit longer. Okay. Oops. Okay. So basically, let me go and see if I can find some better. Ah, here we go. Okay. So we're going to have one hole there. Oops. One hole there. Trying to get this. Anyway, sorry, I apologize for that. We're going to have one hole there. We're going to have one there. And bear with me. And we're going to have one there. Okay? So we're basically, they're all going to be the same diameter and all that. Now, as far as, okay, as far as distances goes, well, I like to leave here an edge distance of about 35 millimeters. Okay. I like to leave a spacing here, a gauge distance between the 80 millimeters. You should use anywhere between 75 and 80. In other words, 3 like the 3 inches gives me 76. I use 80 here. So each hole is going to be spaced at 80. This one's going to be at 80. And the last one's going to be at 35. So that's how I determine one dimension of the plate. Now, of course, this here is going to give me a total of, if I did the math correctly, this should give me 390 millimeters. Okay. Now, what I like to do is I like to leave also a 35 millimeter here. And of course, where the beam is going to end here, in other words, I should draw this in another color. Well, I should do it in green so it's the same color as green. So where this beam is going to end here, and here, so on, okay? So here, I'm going to leave another 35 millimeters. Now, the standard distance that you leave between these two things is about 10 millimeters, okay? So I'm going to leave 10 millimeters to the edge of the next beam. So here's the next beam next to it. So there's going to be 10 millimeters there. And this, guys, is a question of choice. Like, in other words, there's no real, so I made this length here, okay? I made this 80 millimeters.
Sir,
Yes.
I'm having visualizing what that green dotted line is.
That's the edge. This here is, sorry, I should do green with green, okay? This line here represents that line there, and that line there represents that line there. In other words, that's where the two beams are next to each other, and this plate's going to be connecting the two beams together.
Okay, thanks.
Okay? So now what I have here is, of course, I've got one dimension, and I've established the other dimension. Now, what's going to happen here, I'll do this in, probably in blue. How's that?
Sorry, sir.
Yes.
That 80 millimeter that you just drew
Yeah.
until the end of the plate, like until the end of the weld.
In other words, well, that's what I'm getting at. So therefore, this is going to be completely welded here.
Okay, so it's until the end of the plate. Okay.
Okay,
Perfect.
so this is going to be completely welded here. This is a weld here, okay? So this is all welded up to the end of the plate here. You should go back to green so that you guys can, okay? So remember, this here, okay? Now, so with this, okay, I can start determining, like, based on the fact that I have to transfer 333 kilonewtons, I can start calculating what size of weld do I need here in order to be able to resist that 333 kilonewtons. Now, what I want to show you is, I'm going to stop sharing here because I need to show you something else, okay? Now this here, so that you guys can understand, okay? This weld group, okay? Well, I'm in blue. I'll draw it here and then I'm going to erase it. So this is, oh, no, green. I want blue to represent the weld, okay? So this here, this is the weld group here, okay, that I'm drawing here, and the force is here. So therefore, there's an eccentricity between the weld group and where the force is applied. So you've got all kinds of different ways that this thing is be subjected to. And what the handbook does, it gives you a very nice table on how to calculate what this weld site has to be based on your geometry and all that. And that's what I'm going to show you now. So I'm going to stop sharing. First of all, I'm going to stop sharing this. Mind you, this is going to be messy, but I'm going to stop sharing this. And I'm going to show you, I should have sent you this, but I sent you only one. Oops. Oh, sorry. Okay, so this is one of the pages in the handbook, okay? Now, what this does is that it shows, there's a whole bunch of different weld groups, okay? Now, here's one of them. Let me get to it, okay? So here what happens is that if you can determine, for example, well, what we have right now is that we have this value here from our geometry. In other words, we can determine what the value of K is, because we know this length here. So we know that from our geometry, we know that we have a length of 80. So this length here is 80 millimeters, okay? And from this, don't forget, L is always this dimension here. So therefore we have, I'll do it here, it's better. And I like to change color here. Yellow works well, okay? So we know that from our geometry that this length here is 80 millimeters. That's like where we started the weld to where we turned the weld. So this is our weld group right here. So here we have 80 according to our geometry, okay? And that's why this is pretty much up to you. You could have made it 90, you could have made it 100, it's up to you. I made it 80. Now, from here, I know that here I have this thing, KL is equal to 80. In other words, it's equal to this dimension here, and this is 80 millimeters. And L, of course, is the length of my weld, and that was 390. That's where we had figured out the length of the plate, the height of the plate, 390. So I put K times 390 millimeters is equal to 80, and therefore I can determine my K value. So K would be 80 millimeters over 390 millimeters, and of course it's just a ratio. If I do the math on my calculator, 80 divided by 390, I end up getting approximately 2.05. But let's say we have 0.2 for K, right? Now, so that means that here are all my K values here. Let me just change color. Here are all my K values, and I have a K value of 0.2. Now, if you go to the bottom of the table, you see here, it tells you what the value of X is at the bottom of the table, okay? So once you determine your K, you go to the bottom of the table and you get your X value. So once I got my X value, well, it's going to allow me to calculate this little distance here. Okay? So basically, if I want to calculate, in other words, if I want to calculate where the centroid of my well group is with respect to the edge, that's going to be X times L. So for me to calculate this little distance, so right now, X times L is equal to 0.029 times my L, which is 390 millimeters, and therefore that little distance from the edge to the distance of the center of gravity, X is going to be equal to, excuse me, 0.029 times 390. So my X value is going to be about 11.3 millimeters. So that's the distance from there to there. That's where the center of gravity is going to be. Now, if I go back and I want to calculate my A value, well, now that I've got all the information, I'm going to go back and show you how to calculate the A value.
Sir,
Yes.
where do you get exactly the 0.29?
Right at the bottom of the table. I circled it.
So once you get like the K,
Once I get my K value, in other words, once I know where I am along here, then I go all the way to the bottom of whatever column I'm working under, and it's going to give me the X value in proportion to the K value.
Sir,
Yes.
the X, I think it's supposed to be 113.1 instead of 11.3.
It can be.
0.29 times 390?
Yeah.
That gives you 113.1.
0.029.
Oh, it's 0.029? Oh, my bad.
It's 0.0, like this is a zero here. I didn't put the first zero. But if you look at the bottom of the table, it's 0.29.
Oh, yeah, my bad.
It couldn't have been, first of all, it cannot exceed this length here. So that's why I know that, you know, like right now we only have 80, and therefore the center of gravity of this group cannot be out here somewhere. That's number
It's all
one.
good, thanks.
Okay, so 11.3. So now that I've got that, 11.3, I can go and calculate my A. Okay, how do I calculate my A? Well, it's very simple. I look at what I had in terms of overall length, right? This is my force P, right? And I know that my force P, we left, I don't even bother to put that one in. I know that I had 35, I left 35 millimeters there to the edge of the member. I know that I had 10 millimeters between the two beams. And then after that, I came over a total of 80 to the end of the plate. We all agree?
yeah.
So therefore, what's my A value? Okay, so my A value, I'm going to do it up here. A would be equal to 80 plus 10 plus 35 80 plus 10 plus 35 minus 11.3. In other words, I'm taking away a little bit from there. So I get 80 plus 10 plus 35 minus 11.3.
How come are we minusing by the XL?
Sorry?
Why are we minusing by XL?
I'm not minusing XL. I'm minusing this little distance here that I calculated with XL. In other words, the center of gravity is right here. And therefore, what I'm trying to do
Oh,
is,
okay, I see. All right.
that's the center of gravity. So
Okay.
therefore, I'm trying to find what this length is here, which is equal to AL, okay?
So A is the distance from the.
No, you calculate A. You're trying to calculate this length here so you can go and evaluate your A. So right now, this is what we're doing. So we're doing the L, I'm sorry, I should have put LA here, okay? Or AL, I should have put. AL is going to be equal to this value here. I'm trying to calculate this length here, which is 80 plus 10 plus 35 minus 11.3. So that gives me 113.7. So in other words, the distance from the center of gravity to where the load is acting, I have 113.7 millimeters. Therefore, if I divide this by my L of 390, I get my A value. I'm sorry, I'm all over the place, but A is going to be equal to 113.7 millimeters divided by 390. So divided by 390, I end up getting approximately 0.3. It's 0.29. I'm going to use 0.3. So now that I got my A value and I got my K value, well, I can go into the table and find my C value. That's what the table gives me. So I'm going to come to the table. So here is my A value of 0.3. Here is my K value of 0.2, and therefore my C value that I get from the table is 0.196. Now, if I want to determine the minimum size weld that I need, I can take my P and divide it by my C and my L, and that's going to tell me what size of weld I need in order to resist that force. So if I want to calculate my D, I'm going to do it here. D is equal to P over C times L. So therefore, this gives me 330 time divided by 0.196 and divided by 390. And that's going to tell me the minimum size weld I need in order to resist that force. So I take 330 divided by 0.196 divided by 390. I get something like 4.3 millimeters. Okay? So in other words, I would use at least a 5 millimeter weld. Okay? Now in my case, in that case, if I make my weld size here, all along here, if I make my D, I have to make it at least 4.3. I'm going to make my D equal to 6 millimeters. I don't care if it's going to be more resistant. I know that that's going to be sufficient. So now I've established my weld size for this connection.
Oh, I have a question, sir.
Yes.
When you looked on the table and you looked at like 0.2 and you went to 0.196.
No, what I did is I first went to my K value, then I went to my A value. And where those two values interact, I got my C value from the table.
Okay, thanks.
Okay, so in other
Just
words,
make sure.
this is my K value, this is my A value. So where those two intersect, that gives me my C value, okay? And once I know my C value, I know my L value, I know my P value, then I can go calculate the minimum D size that I need. So in other words, this weld should not be less than 4.2 millimeters in thickness in order to be able to resist that force based on that weld group.
Right. So what did you got for the value for D then?
What?
What did you get for the value of D?
I got I need at least 4.33 millimeters, so I'm going to use a weld size of 6 millimeters.
Okay.
So I'm going to use 6. I'm not going to use 4. First of all, there's no such thing as 4.33. Weld size starts at 5, and then they go up to 6, and then 8, 10, 12. Okay, so I'm going to use 6. In other words, 1/4 of an inch. I know that 1/4 of an inch weld would be sufficient to resist that force. So that's my weld size, D. Okay, so that's all I need from this table. I hope you guys have this all down. Anyways, it's being recorded. You'll be able to come back. If you don't have you can listen to me. So that's what I got now. Now I got my D. I'm going to stop sharing this. I can get it. I'm going to clear this now. Okay. I'm going to stop.
Sorry.
Yes.
Here. I just wanted to know if when you find your D, when you use your equation P over CL, the
Here,
units aren't supposed to cancel? Yeah.
You're talking about this equation here?
Yeah, like the units don't cancel?
No,
Or-
no, because this is in kilonewtons, this is just like, these are empirical formulas, you understand?
Okay, so it's one of the, okay.
It's one of those
'Cause I was trying to-
empirical formulas that they develop by, by experimentation, so, you understand? The only time the units work out is when you're looking at these ratios here, A, K, you understand? Because that's the only time the units cancel out, okay?
Okay.
The C value is in kilonewtons per millimeter?
Well, like it didn't, like here, it just says coefficients tabulated below, that's what C is.
Okay.
D is the size of your field well in millimeters. So if you do it correctly, you'll end up getting a D size in millimeters, okay? L has to be in millimeters, that's what we've been using. And P has to be in kilonewtons, so that's what we've been using. As long as I use, okay, the distance of the vertical well to the central, that's what XL is, understand? This here, okay? So as long as you're using all the correct units to do the calculations, then whatever we get from this table, our D here is going to be in millimeters. That's all I care. So the table has been based on those units, okay? So now I've got my D, right? Now I'm gonna stop sharing this. I don't need this table anymore. I know I need a D of 6 millimeters. Stop sharing. Let's go back to, where were we? Oh, did I? Oh, I lost my drawing, right? I did that on the whiteboard, right? No, on the whiteboard here. Share. Well, here we go. There we go. Okay. So now, guys, we're back to this, and we'll use this to do our calculations. I don't want to redraw this. It's kind of hard. Okay. So now, I know that D is going to be equal to 6 millimeters. Okay. And I know that according to good well practice, the thickness T, okay, like in other words, D should be equal to T minus 2 millimeters. In other words, the well size should be 2 millimeters thinner than the material that I want to use. So therefore, I know that the thickness of my plate here, the thickness of the plate here, T is going to be equal to 6 plus 2. So I'm going to start with an 8 millimeter plate. Okay, so that's what I'm going to start with. So now I've established the thickness of my plate. So that's my plate. Now, excuse me. Okay. So now from my geometry, right, the only thing I have to be concerned about is, I'm going to try to change color. What color should I use? Let me use the yellow.
Sir, is there a reason why you add 2 or you?
Oh, that's the, if you remember from the welding lecture we did 2 weeks ago, sorry, last week, the weld should be 2 millimeters thinner than the material that you're connecting.
Okay, perfect. Thank you.
So in other words, D is T minus 2. D is T minus 2. Therefore, the T should be at least 2 millimeters bigger than my D. I've established my D to be 6. So 6 plus 2 is 8.
Okay, so therefore, if you have the thickness of your plate, then
then you work it back. Well, no, if you have the thickness of your weld that you need, then you can go and calculate the thickness of your plate.
Okay.
You follow?
Yes.
What they're saying here is that when I'm welding this, okay, well, like in other words, I'm trying to see what's the best way for you to see it. Okay, they want to make sure that the weld stays at least a couple of millimeters below the edge here. Okay, so this is where you get your D is equal to 6 here. I'm sorry, I'm trying to draw this at 45 degrees. Okay, so that's what they're trying to make you do. Okay, now this is not rolled or anything, so therefore we don't have to worry about 0.75 times the thickness. This is going to be a plate, so it's going to be cut straight. So I don't have to worry about the fillets here. If it was a fillet, then D should be 0.75 of that thickness. That's the other rule. Okay, like we did this morning in class. Now, once I've done this, well, pretty much, okay, what's there left to do? Well, I have to look at 2 other things. Okay. Okay, number 1, okay, is I've come up with 390 millimeters here. Well, I got to make darn sure that it fits in here. Okay, it fits in here. But I went to check in the table. Okay, right now in the table, you get this big T value. The big T value, to make you understand what the big T value in the table is, if I look at a cross section of a white flange like this, okay? If you look at the cross section of a white flange like this, okay? You know that there's a fillet in here, there's a fillet in there. So therefore, you want to make sure that your plate, does not butt up against those fillets, okay? So this is my plate here of 390. Well, according to what I found in the table, I did this for you guys, okay? I have here a distance of 530 millimeters, because this is a 610, remember? On the average, this is a 610 by 88, this is a 610 by 113, this is a 610 by 101. So therefore, I know I have ample room to put my plate in here, and I have ample room to go and weld on both sides. The other thing is, I went to check the thickness of the web. The web here for this one here is 10 millimeters, which is thicker than my plate. So whatever's good for my plate will be good for my web. The web on this side is 11.2 millimeters, so I know that's good. And I know, so in other words, this is 11, this is 10. And on this side here, the web is 10.5. So I'm sure like all my webs are thicker than all the material I'm using for my plate. So therefore, when I'm going to be checking the bearing for the plate,
Sir.
checking the failure of the plate, since it's thinner than my webs, I know my web will not, I won't have to go and check the web. Now,
Sir,
yeah.
like is the height or the T value the same for both both girders or?
oh no, like they're very, very close. This one here, like this one here, the W610 by 113.
Right.
The T value is 529.
529.
This one here is 530.
530.
That's for the W610 by 82. And this one here is 530. So they changed by about a millimeter, you understand? Because they're all W610s.
Okay.
Okay. Now, the next thing you have to do, of course, is, okay, now that we've calculated everything, we just have to check two things, or three things. One is, let me put this in red because it's dangerous, okay? Now, we have to see if we have enough resistance here, okay, like this, so that this thing does not break off. You understand? Just like we did in a regular connection. In other words, this here would be failure plane number 1 and failure plane number 1, okay? So, can I erase some of this stuff? Yeah, I think I should make myself some room. Where's that eraser? Erase it, okay. Well, I shouldn't erase the 390, we need that. Okay, so this is going to be one failure plane here. Okay, that's one failure plane. And then there's going to be a second failure plane that we have to check. So there's two things we have to check for. Is the failure plane, 1, 1. And after that, there's another failure plane that we have to check for. I'll do it in a different color so you guys can see it, okay? And then the second failure plane is like it fills in shear right across here. So those are the two failure planes that we have to be concerned about. Now, and this will become 2, 2. So now I know that, excuse me. So here I have the failure here is in tension. So therefore, you know, the formula that you have to check this, you know that the formula is TR is equal to phi U, and then big brackets, okay, UT AN FY plus 0.6 AGV FY plus FU over 2. So that's the equation you're going to do to calculate that. I'm not going to do a calculation. I'm just going to tell you what you have to use. The value of phi u, we know that that's equal to 0.75. The value of ut, okay, in this case is going to be 0.9. So that's the value of ut. the value of AN here. Well, what is AN? AN is equal to this dimension here, 35, minus 1/2 the whole diameter, because it's going to be from there to there. So what is the whole diameter? Well, we decided to use 3/4 inch bolts, so therefore we have 19 millimeters. Now, we're not sure if we're going to be drilled or punched, so therefore we're going to add 4 millimeters, okay, divided by 2, okay? So that's this dimension here, and then of course you multiply this by T of 8 millimeters, and that's going to give you your AN for here. So that's where you get the value for there. And then of course your
What was that
AG,
last step?
sorry?
What was that last step to getting AN?
Well, AN is half the bolt hole. In other words, it's 35 minus half the bolt hole. So in other words, it's this width here, W, multiplied by T.
Multiply by thickness, right? Oh, okay.
Okay? So that gives you your AN value for here. And of course, that's the one that's in tension. And here your AGV is very simple.
Are we sticking to a thickness of 8?
Yeah, we decided we're going to try an 8 millimeter plate, see if it works. So far, you know, like that's what we're checking now. We're checking to see if we're going to have a problem with the block shear. Okay? And if we don't have a problem with the block shear, then we can use an 8 millimeter plate. Now, this length here is your value of AGV, your gross shear area, and basically that's going to be 80 plus 80 plus 80 plus 80 plus 35 multiplied by your thickness. That's your AGV. And you put all the values into your equation, and if that TR value is greater than your VF value of 333 kilonewtons, then we know that this is not going to be a shear problem. So that's check number 1.
Sir,
Yes.
do you mind repeating TR, please?
If what?
Do you mind repeating TR, please?
TR. TR is the equation. In a sense, TR is phi in big brackets UTANFY plus 0.6. This is, you find this in your notes, you understand?
Yeah.
0.6 AGV FY plus FU divided by 2. That's the formula for block shear, okay? So that's where you get that equation there. Now, when you're doing it for, I'm going to erase some of this stuff that's getting very messy. Let me just erase some of this stuff. Okay. Now, then after that, you're going to be checking for failure plane number 22, and that's basically just going to be very simple because all you have is an AGV here, okay, for 22. So this can be very easy to do. So you know your TR for failure plane number 22, TR, this is 2, okay? It's still going to be equal to phi U, this is phi U. And of course, in here, all you're going to have is 0.6 AGV, because you have nothing in tension, FY plus FU over 2. And your AGV is going to be very simple. It's simply going to be 80, well, it's going to be, it's the length of your plate, 390 millimeters, times your thickness of 8 millimeters. There you go. So you do both checks, and if both TRs end up bigger than 333, that's good. Then the very last check you have to do is just to check the bearing of the bolts here. And therefore, what you have to do is that BR is equal to, and I want to get this value from you from the table, and you guys can just do the calculation. The BR value, okay, BR is equal to, let me see if I can find it. I wrote it somewhere. Just give me a second. Okay, the BR value for a 3/4 inch bolt and for an 8 millimeter plate, the BR value is 165 kilonewtons per bolt, okay? And of course here, I multiply this by 5, so I'm gonna have, wow. I'm gonna have something in the order of 825 kilonewton, and that's greater than 333 kilonewton, so I know that my bearing is good. And if the bearing is good for an 8mm plate, then the bearing is going to be good for a 10mm web thickness. So I don't have to worry about the bearing onto the web. And once I've done all those calculations, that's done. And then I just transfer all this information onto the drawing. So the drawing, you're going to show that you have a plate size this big and all that. That you actually show the detail of the spacing here in between the two beams, you know, and all that. And there you go, guys. Isn't that fun? A little messy, but
That was actually easy to follow.
sorry?
That was actually easy to follow.
Yeah, it is easy to follow, and if you wrote it down as I was talking about it, you can go back. And like I said, the only two calculations that you have to do right now is this one here for failure plane number 1, 1, and then do the one for failure plane number 2, 2. I mean, failure plane number 2, 2, if I do it right now, it should be very easy. 4, 5 times 6 times 390 times 8 equals times 75 equals. Wow, not a problem as far as my calculations go.
Sure.
Yeah.
The AGV for both 1, 1 and 2, 2, they're both the same, right?
No, because the 2, 2 goes all the way up here, and the 1, 1 stops there. So, like the length here is 390 for the 2, 2, but for the 1, 1 it would be 390 minus 35. Because like
Top and bottom, or just the top?
Pardon?
Because you've got two 35mm dimensions.
Hold on a second. Let me just, so that you can see what I'm saying. So we're talking about this one, Andy, right? Andrew?
Yep.
1, 1 here, right? Okay. So in other words, we're saying that it can tear apart here and shear off here. So here I'm going to have an AN value because it's in tension, but my AGV value here, okay, goes from here down to there. So therefore it's 80, 80, 80, 80 plus 35.
I catch it. Okay, thank you.
Okay, and then the other one, because it's going to shear right across, I have no tension, therefore it becomes 390 times the thickness.
Sir,
Yes.
at the bottom of the page, is that BR?
Which one? Yeah, this is BR. This is for bearing, to make sure that the bolts, when they're resting, when they're going to be resting on this plate, we don't have any possibility that it's going to yield.
Okay, do you mind going through the calculations again? Because I can't read it.
Well, you're going to get the video, you're going to listen to the video,
No, but sir,
take a step by
even
step.
if I go back and read and watch the video, I still won't be able to read your handwriting. So.
Oh yeah, but what you do is like you basically, you start the video, you listen to my voice, you stop it, you write down the value.
Okay, never mind.
Is that okay? I mean, which numbers do you want me to go over? I can go over any number you want. It's just that it's very hard to write with the mouse, you understand? Unless I can.
What's the value of FU?
Well, if it's 300 FY, the FU is 450.
All right, thank you.
Now, Jared.
Yeah.
Okay, so is there anything you want me to go over right now? So this way I can clear it up for you, because I know it's a little bit messy.
No, it's okay.
No, like go over your notes and tell me which parts you don't have, and we'll fill in the gaps.
I guess just like TR for like section 2.2. If you could just like walk through that one more time.
Okay, in other words, for this one here, right? Okay.
Yes.
Well, look, what I'm going to do, Jared, I'll try to make it a little bit neater. It's just like I'm trying to get through it. Okay, don't worry about this. We're not worried. We have time. So let me erase this here, okay? Like the equations, unfortunately. Okay. So you want me to go for 2, 2 here, right?
Yes.
Okay, so here, I'm going to try to. Okay. So when I have, first of all, Jared, when I have block shear, Okay, block shear, it doesn't matter, okay, how it's gonna block shear out, but the equation is TR for the block shear is equal to phi U, big brackets, utility factor, UT, AN, FY plus 0.6 times AGV. This is FY plus FU over 2. Do you recognize the equation?
Yeah.
Okay. So what this equation does is that when you have block shear, in other words, when something can pull out somewhere like this, okay? In other words, it comes out as a block, right? The first thing you have to worry about is that which side of that block shear is in tension and which side is in shear. That's what you have to be concerned about, okay? So for example, if this is being pulled out here, I'm just giving you an example. This is being pulled out here. Then this side here is being pulled away, okay? So this becomes tension. And therefore, let me change color so you can see this, okay? Since this is becoming tension here, okay, then it's only this side of the equation that contributes to the resistance. Here, because it's being pulled here, I have shear here. I'm going to change color for shear. Let me just erase this. Okay, so here, let's do it again. Okay, so here what's going to happen is I have shear here, and so here the material is resisting in shear. So once I can calculate this length here and this length here, it's this side of the equation that contributes to the resistance. Is the equation clear now? So this is for all the lengths or all the segments that are in tension. These are all the lengths that are in shear. Okay. Now, you wanted me to do it for number 2. Is that what you said? You asked me, Jared?
Yeah.
Okay, so here. So now, if you look at the equation, okay, let me erase something here. Okay, let me erase the example I was trying to show you here. Okay, if you look at the equation, let me make it in red. Okay. Okay. Here, what's happening is that it wants to fill right down here. You see it? Is that okay? You understand 2, where it is? It's filling right across the plate, right? So if I look at my plate here, okay? If I look at my plate here, where all the holes are, okay? The only resistance the material has is in shear. So therefore, for 2, this part goes to 0. I have no tension, so therefore I only have to worry about this side of the equation. So therefore, this stays at 0.75. This stays the same. The only thing I have to calculate is my AG. So my AG would be the total length of the plate here, which is 390. So my AGV, my gross cross-sectional area for shear, would be equal to 390 millimeters times the thickness, which is 8 millimeters. And that's what goes there. And then this, and therefore, and if this value of TR ends up being more than 330, and I just made a calculation, and according to my calculation it's supposed to be, then you're okay. That's not going to fail on you. Jared, I need to know some kind of sign that you're still with me.
Yeah, I understand. Thank you.
So is that clears up 2. Did you understand? Yeah. Now, do you understand why for 1 we add this little part here, because we do have a little section of that block shear that will be in tension.
Yeah.
And that's why we have this little section here. So that's what you have to, so when you look at this equation, first you can determine which segments are in tension, which segments are in shear. That's the first thing you have to determine. Then once you see that, then you can go and plug in the values into the equation. So you'll know what to calculate for AN, you have to know what to calculate for AGV. Okay?
This
Thanks.
Yes, next question.
just want to be sure, but like we chose the FY to be 300 MPa, right?
Well, in this case, the plates are still they're still being produced in 300 MPa, so you use an FY of 300 MPa. Yes.
Okay. Thank you.
Okay. As a matter of fact, the beam's going to be in 350, so it would even be higher. So I'm not worried about the beam failing in shear.
So should I stick with 300 or just like?
Yeah, because you're always calculating for the weakest element in your connection. In this case, it's not the web; it's the plate itself.
Oh, okay, I see. All right.
Okay.
Thank you.
Okay, so is that clear? You got everything here? Because what I did after that, okay, I want to talk to you about the other connection. The other connection I want to talk about today is, of course, the connection you're going to have to make for that vertical brace. And I sent you guys a PDF through Leah, but I'm going to pull out the PDF. Okay, I'm going to clear the drawing. Stop sharing. Okay, so where's my PDF? There's my PDF. Okay. Now, this is what I sent you guys through Leah. Okay, this is the example. Okay, that I'm going to go through it with you guys so that you know what to replace in here. But this is what you're going to have to do. Like, I'm going to try to draw what so you guys can relate to this diagram. Okay, so you remember we calculated. Okay, so we went through the trouble of calculating. Okay, the two vertical braces here, and you guys were supposed to have sized them already based on the fact that this was in compression and you had a length here of so much. And somebody told me, so does anybody have the size of the HSS for their brace here? If you don't, well, that to me is very secondary. That's something that you're going to have to go and determine. So here, this is your HSS, okay? Not this one here.
What exactly are you doing right now?
This is the braces, the vertical braces up for the building. In other words, you're going to have to be able to connect these braces. You're going to have to be able to connect these braces to your structure. In other words, you want them to work together. So I'm trying to show you how, this is the example that you're going to use to be able to do that. And you've got all the information. We've done everything in class. So here, I'm just giving you the step, like this is a good example. So for example, here what they're showing you is that if this is your HSS that you're going to be putting diagonally, the vertical brace that you're going to be putting diagonally to brace your building, okay? What they're saying is that you're going to have to put a plate in here like this, okay? You have to put a plate in here like this, and then that plate is going to be then joined to another gusset plate that you're going to be welding to your column here, okay? And then those are going to be bolted together. So the first thing you have to do is know what is your TF force that you have to resist and calculate the number of bolts you need here. So that's what you're going to have to do, okay? So you're going to need to put like, I don't care, like here, if your plate's going to be wide, you can put your two bolts like this, okay? It's up to you. You can put your two bolts side by side, or it depends. So you first calculate the number of bolts you're going to need to be able to connect the two plates together here. Then once you did that, you can decide, for example, you can put the bolts like this, okay? And then after that, this example shows you, like, how do you, like, for example, in your case, okay, if you decide to put the bolts side by side, just like here, okay, on your plate, if you decide to put them side by side, then you can follow this example the way it, and this, here's my HSS, like this, okay? So if you decide to put your bolts side by side like this, and guys, even if you need one bolt, you should always provide at least two bolts, okay? And I use, like, in other words, use 3/4 inch bolts for everything. That's the standard bolt size. And of course, as far as edge distance go, I like to use 35 and 35. So that's going to tell you how much of a distance you have here. And then you'll be able to do, so you'll be able to do all these calculations here, okay? So this is the example I send you so that you guys can calculate everything you need so that you can do the calculation for the plate, for the vertical, I should say, for the brace that's going to get connected to the to your structure. And if you want to see how that's going to get connected, well, you can go to the sample drawings. There's a couple of them that have detailed that can give you an idea. Well, maybe I should pull up the sample drawings. Let's see. I'll go find the sample drawings and maybe. So this is now what I want you guys to do is I want you to go through this example. I'm going to stay here, and if you guys have any questions whatsoever. Okay, so here they always try a plate size of 12 by 128, okay, and all that. And then they check, for example, if here is strong enough. Like I said, the dimensions of this is going to be based on your geometry. So once if you haven't worked out your HSS yet, you cannot do this detail. So the first thing you got to do is go determine your HSS for your brace. Determine what size you're going to use. Determine what thickness of wall thickness you're going to use. And that's also going to determine the thickness of the wall. Is also going to help you determine what is the size of weld that I can put across here, because you should not put a weld size thicker than the wall thickness. Like you cannot put, like for example, if the wall thickness of your HSS ends up being, I don't know, let's say 3.2 millimeters, you cannot use a 4 millimeter weld. You have to use a 3 millimeter weld, and therefore that's going to dictate how long this length is going to be. So everything is going to be a result of this choice here. And I don't know what that choice is. That's something you guys have to do. So that should be designed by now, because we did this last week. You should have already chose this. And once you've chosen this, based on the geometry here, you can determine what's the length of the weld here. Remember that once you calculate this weld here, it should not be less than 38 millimeters. If you need less than 38 millimeters, you make it at least 40 millimeters. You go through good welding practices. So in other words, review everything we've done in the lectures and so on, and look at all the different things that you have to verify. And once you verified it, if everything works out, then your connection is okay. And like I said, I have no idea what size that HSS is.
Sorry, you said that we designed the HSS last week?
Well, I gave you the length, I gave you the force the compression force for the thing, and you had to go to the table and find the HSS. That should have been done between last week and this week.
Yeah, I got a 114 by 114 by 3.2.
See, so that's good. You see, so now you know what to start with.
That was like Andrew. That was like I think like 2 weeks or 3 weeks ago.
That was 2 weeks ago, right?
Yeah, I think it was probably 2 weeks ago.
All I'm saying is that we did the vertical brace. Yeah, it was two weeks ago, because that's when we did the wind on the building and everything. That's right.
We did everything. We just didn't get the size. We had all the numbers. We just had to go on the table. But
you had to go on the table. We had a length because we got the length from ADA, and we went to the table. So what you're saying right now, Vincent, you've got a 114.
114 by 114 by 3.2.
Okay, by 3.2. See, you see what the 3.2 tells you, Vincent? Is that the weld that you're going to be putting here, okay? The weld that you're going to be putting here cannot be greater than 3 millimeters.
Okay.
Because you should not have a weld thicker than the material that you're joining.
So if we get a weld that's more than 3.2, it doesn't make sense. It's not good.
Or you work it the other way around. You try to find a value of the weld for a 3 millimeter weld. I don't know if the table gives you that. Okay. Does the table start at 3 millimeters, or does it start at 5 millimeters?
I don't know.
If you use a 3 millimeter weld, right? You can still use a 3 millimeter weld. The only thing is that you're going to have to calculate the VR from your equation. If the table doesn't give it to you, then you can calculate it from the equation. And I'm not sure. I think the table only starts with a, let me see. Let me just take a look at what the table starts with. Yeah, the table that I gave you starts with a 5 millimeter weld. So if you want to use a 3 millimeter weld, Vincent, we'll do the calculation right now, okay? What the VR value is per millimeter. Sounds good?
I mean, if somebody can verify that maybe they
Well,
have the
look,
same.
Mason, I don't doubt that that's not a good number.
I'm going through my notes. I'm pretty sure that's what we had. The number rings a bell.
It rings a bell, Kaylee?
Okay.
Yeah.
Okay, so you can still stick to a 3.2, okay? The only thing is that since you can't use the tables, it's not that difficult to calculate the VR value, okay? So guys, look, I'll do it here, and then you'll have this VR value if you happen to use a wall thickness of 3.2, okay? So
Because there was another one that was exactly like a 114 by 114. I think it was like a 6.4 or something like that.
oh, see 6.4, then
And
you
it worked out too, I'm pretty sure. So I don't
Oh,
know if we can just
but-
choose
but-
that one instead.
like, Vincent, you don't change your member size because the table doesn't give you a VR value. You know what I mean? You know, in other words, you're gonna go change your thickness of your wall so that it can match whatever you can find in the table, right? But I just want to show you that if you want to use the 3.2, right, then the VR value for a 3.2 is very easy to calculate because you're going to use a 3 millimeter well, okay? And 3 millimeters is common. It's not that it's uncommon, okay? So if you want to use, so the VR value, here's the equation, okay? The VR is equal to 0.67 times phi W times X U. And then of course, I'm going to keep writing it down here. And then here you have 1 plus 0.50 sine raised to the 1.5. I don't know why I'm putting this in. I'm putting it in anyways, okay? Theta, and theta is the angle, okay? Times MW, okay? Now, this is the equation you have for VR. So now, this is 0.67, phi W is, so therefore, this is 0.67. So I have 0.67. The phi W is also 0.67. That's the reduction factor for welds. Okay. The XU is 490 MPa. That's your XU. This here goes to 1 because when you what's the sign of 0 degrees? That's 1. Therefore, this goes to 0 here. Therefore, this only becomes 1. So this whole place goes, okay? If I do sine of 0, that's 0. So therefore, this goes to 0. I have 1. And here the MU is very simple. I don't have a weld group. I only have a weld there and a weld there. So that this goes to 1. So therefore, that's the value of the weld per millimeter, okay? Oh yeah, sorry, the area of the weld. I forgot the area of the weld. AW. Where's my AW? I forgot the AW. AW. Okay. Now what is AW? Well, it's very simple. I forgot the AW. Okay. I got 3 millimeters there. I got 3 millimeters there, and therefore this is the area of the weld. Therefore, that value there is 0.707 times 3, okay? And that gives me times, of course, the length L, okay? And that's what you want. This is per millimeter weld. So if we do the math, let's do it together, Vincent. See what we get. 0.67 squared times 0.707 times 3 times 490 equals divided by 1,000 to bring it to kilonewtons. So I get a value of 0.4. I get a value of 0.466 kilonewtons per millimeter. So the VR for your 3 millimeter well is going to be equal to 0.46, well, almost 467 kilonewtons per millimeter. Okay, and there you go. And that's what you're going to use for your VR. And you don't have to change your section now. Right?
Okay.
Then once you know what your force is in here, don't forget you're going to have 1, 2, 4. You're going to weld this on 4 sides, okay? And you'll be able to determine what's the length that you need here to attach your HSS to your plate.
The AW, how did you get that again? You did
Well, the AW is very
0.707?
simple. Like, for example, when
Why
we
is
talk about the AW, right? Like, if I look at a weld, a fillet weld, okay? This is, okay, let me draw it the other way around. So this way. I'm going to draw it. Let me draw it the other way around. Okay. So a fillet weld is basically like a triangle. You understand? Okay. Fair enough. So your AW is the length of the throat here, multiplied by the length of the weld here. This is the length of your weld, and the thickness of your throat. You got that? This is the area of the weld that's going to give you resistance right in here, the one that's, okay? You see that? Okay. So therefore, if this here is 3 millimeters, right?
Mm-hmm.
Well, I know that this is 45 degrees, right? If this is 3 millimeters, and therefore this is the cos or the sine of 45 degrees, which is 0.707.
Mm-hmm.
Therefore, this length here is simply, pardon?
How did we determine the length of the fillet?
I'm sorry, John Michael, you got to come in a little bit closer to your speaker because I can hardly hear you.
How did we figure out what was like the thickness of the weld or fillet or whatever?
Well, because he said that he had a HSS that is 114 by 114 by 3.2 millimeters.
Oh, okay, I see.
And therefore, you should not use a weld that is bigger than the thickness of the material. Otherwise, you might burn right through it.
Right, okay.
And therefore, since he has 3.2, we're going to use a 3 millimeter weld. And since the table didn't have the value, the VR value, we just calculated what the VR value is for a 3 millimeter weld. Understand?
Okay.
So, Vincent, do you understand how I got this length here?
So it's 0.707 times 3?
Yeah, like on your calculator.
Oh.
Like, look, this is just math, okay? So in other words, when we're talking about a 3 millimeter weld, this leg here is 3 millimeters, and that leg here is 3 millimeters. You agree? And the area of the weld is really the length of the throat here, right?
Yeah, okay, makes sense, yeah.
So this is 45 degrees, right? So this is the hypotenuse, therefore it's either the sine of 45 or the cosine of 45. They're both the same, which happens to be 0.707.
Mm-hmm.
Okay, 0.707 is the cosine of the sine of 45 degrees, and you multiply that by the hypotenuse of 3 millimeters, and that's going to give you the length there. Does that make sense?
Yeah, 2.121.
Yeah, and that's the length of that. That's the length. That would be the length of the throat of your weld. So
And
here,
then you have to multiply by your length.
yeah, and then of course, for each millimeter that you get, that's going to give you that resistance of whatever we calculated there, 0.464. Now, if I look at the table, Mason, right, a 5 millimeter weld gives me a value of 0.778, and a 3 millimeter weld gives me a value of 0.467. I think we're pretty much on the right track.
Makes sense, yeah.
You see? And if we
Sir?
Yes.
What's the length of the weld?
Well, that's what you have to determine. Once you know what your force is here, right? Once you know what your T is here, then you have to determine how much weld do I need to be able to resist this. So the length is what you have to actually calculate. Now, if I'm not mistaken, let me just see something, okay? Now, the first few, okay, so this is just to show you the things you have to check for, like the block shear here, the shearing across here. It all depends on the number of bolts that you're going to need. And like I said, if you calculate the number of bolts and you end up with one bolt, make sure you provide at least two. You never put a one bolt connection. And clear drawing, okay. And I believe that this is where they start. Here they even try. You don't even have to try. I would actually calculate, you know, what the length that I would need, and then I would use multiples of 10. So here they're just trying to show you that in this case here, this is what they needed. So the length of the weld is exactly like we did in class this morning. Okay, it's very good. Like all you have to do for the length of the weld. If I redraw here is the H weld. Here's a plate that I'm going to be inserting into the HSS like this. I'm going to try to draw it so you guys can see it. So here's my HSS. And here's a plate that's going inside the HSS. And there's my HSS and the HSS. Does everybody understand what I'm trying to draw here? Okay, so basically what's happening is that this plate is going to, like, in other words, if I look at a plan view of the HSS, this is the HSS here. They're going to cut a slot in here like this, right? Okay, and then they're going to be inserting your plate right in here. Okay, this is going to be the plate. This is this plate here. It's going to go right in here. Okay, and then what's going to happen is, I'm sorry, yeah, like that. And then what's going to happen is it's going to be welded here, and it's going to be welded here, as well as here and here. So therefore, you're going to have 4 weld segments. So therefore, I can multiply that value by 4. Do you guys remember what the TF value was in the brace? Does anybody have that value?
Which one?
Like what was, like when you size your HSS, what did you use as a CF value? Because the CF value and the TF value are the same.
Let me go check.
51.3 kilonewtons.
Sorry?
51.3 kilonewtons.
I didn't hear that. I apologize. 31?
51.3 kilonewtons.
Yep, 51.3 kilonewtons.
51.3 kilonewtons. So it's not a big force. Is that what we're saying? Okay, so here we go. Now we know what we have to design for. That's our TF, 51.3, okay? Now, so I know that if I use a 3/4 inch bolt, one bolt is good for 79 kilonewtons, even if the threads are intercepted. So therefore, I know that if I put 2 bolts, example, so right now I'm going to be putting 2 bolts. I've already calculated the number of bolts I need, because I need less than 1 bolt. And I never put a 1 bolt connection. So I'm going to be putting at least 2. Now, as far as this length here, can somebody tell me, what was the VR value that we calculated for the 3 millimeter weld?
0.467 kilonewtons.
Okay, so the
per
VR
millimeter.
is 0.467 kilonewtons per millimeter. And I know I'm going to have 4 segments, so I can multiply this by 4. Okay, so 0.467 times 4. So I'm going to, for each weld that I put there on the other side, top and bottom, I'm going to have a VR of 1.868 kilonewtons. So therefore, what's the length I need per millimeter? So if I take 51.3 divided by, I need 27 millimeters. So therefore, and I know that the length of the weld should not be less than 40. So therefore, all I need here is 40 millimeters of weld. And that's it. Because I end up getting 27 millimeters. They're not big forces. So all I need to do is, and I know from good practice that this weld should not be less than 38 millimeters. I say 40. So there you go. So right now, this is going to be 40 millimeters into it. The distance from there to there is going to be 35. And the distance from here to here is going to be 35. There you go. So we've established what our geometry is. Now all you have to do is determine the thickness of your plate. And that's what these calculations are all for. And then, like, I would definitely not use anything more than, I would try a 6 millimeter plate as a trial section and see if all these calculations work out for you. Okay?
Sir,
Yes.
Can you repeat how you got 40 millimeters? Sorry about that.
Well, look, I have a VR here. We said for a 3 millimeter well, I have a VR here of 0.467 kilonewtons per millimeter. So now I'm going to be having, I'll do this in another color so you guys can see it. Let me see green, okay? I'm going to have a weld here. I'm going to have a weld on the underside there. I'm going to have a weld on this side. So there's going to be 4 segments of weld that I could put to attach this plate to this HSS. Is that something you can see? In other words, I'm going to have a weld here, and I'm going to have 2 at the bottom. So I can provide 4 weld segments to attach this piece to this one. Is that clear?
Yeah.
So therefore, I know I can multiply this value by 4 because I'm going to be able to put 4 segments of weld. And that gave me this value here. This is my VR. Therefore, if I want to know the length, I take the force I want to resist of 51.3 kilonewtons divided by 1.868 kilonewtons per millimeter, and that gives me the length of the weld. And I end up getting 27 millimeters, and therefore you never make, the minimum length that you should have is at least 4. And that's how I came up with 4.
All right. Thank you, sir.
You're welcome. Now, so that's going to be the detail for how you're going to construct, the joint to connect your HSS to your structure. And then at your structure, I'm just going to clear the drawing. At your structure, so what's going to happen now is if you look at an elevation of your building, okay, you have a column here. You have a column here. And you have a base plate on your column. And then you've got your other column here. Okay. And you have your base plate here. Okay. And in this case here, I believe that this is the wing column. I should have made this just a touch shorter. And then you have your beam going across here. So your brace is basically going in here like this. Okay. So if I make a cross section looking down here, okay, what you're going to see is you're going to see the base plate for your column. You're going to see the column itself. And then here you're going to attach a gusset plate that's going to get welded. It's going to get welded to the base plate and to the web of the column. So if I make a cross section across here, so you guys can see what I'm doing, okay? So here's the back flange here. Oh, we should draw this a little bit. Sorry. So here is the edge of the back flange of the column, the edge of the back flange of the column. And of course, here I've got my web member. I got the web of the column in here. Okay. And all of this is sitting on a base plate. Okay. So basically, my gusset plate is going to be going, change color so you guys can see this. Okay, so my gusset plate is basically going to be something like this, that you are going to weld here, and then it's going to have 2 holes, so that when you come and put the plate for your HSS that we just designed, they'll be able to be connected together. If you go on the sample drawings, I think you'll see how that detail works. As a matter of fact, let me go get the sample drawings. Might as well look at it right now. Okay, so I'm going to see if I can go get the sample drawings. here. No, not there. I'm trying to find where I filed the. I'm trying to find where I put those lines. Oh, here we go. I don't know if it's on drawing number 3 or drawing number 4. So it's not on drawing number 3, but drawing number 3, guys, there you see the detail. Let me clear the drawing. Sorry, I haven't shared this yet, but I'm gonna, hold on. And I'm gonna get drawing number 4 at the same time. Okay, so here you go. Let me clear. Okay. Where's my PDFs? Okay, so where am I now? I can't seem to find my PDFs. Oh, here you go. Share. Okay, guys. So, guys, this is the typical drawing. So this is what you're seeing right now. Now, here in this case here, what they did is they put the bolts one behind the other. Okay. Well, you know that in your case, you can really modify that. Annotate. Okay, so here she decided, or he decided, I think it's a she. I think this was Xavier. She decided to put the bolts like this. You guys can put the bolts this way. Okay, so you don't have to do this. And this is the plate I was telling you about that you are going to. She decided to use a 5mm well, right? And thickness of additional plate, 5mm, thickness of gusset plate, 8mm. Anyways, so that's what I mean, that this is your brace here, 114. So she ended up getting 114, but I don't remember what size, if it was 114 by 3.8, I don't remember. And this is how it's going to look like when it connects to the top of the column, and this is what it's going to look like when it connects to the bottom of the column. So in your case here, we decided to put the bolts side by side, so this is going to be slightly different. Okay. Now, for the other, okay, now for drawing number 3, well, here's a detail, okay? Here's a detail that she got for drawing, for the detail. This is the detail of the Gerber, okay? She ended up getting 8mm. We decided to get an 8mm weld also, okay? And she put the same thing here, except she got 3 bolts instead of 5. So we ended up getting 5. So this is very similar to what we have, okay? And that's the detail here. And that's the detail how to, to join this is the drop-in beam here. Okay. So this is the drop-in beam here, okay? And this is the girder on the other side, and that's the cantilever side, and that's what we just finished calculating here, okay? So I don't know why she made these lines extend all the way here. I probably penalized her for that. So that should be there. That should just be. And she kept the same dimensions that I told her to keep. In other words, the edge distance. So we ended up getting here 390. Okay. And of course, what you should do, the best thing to do in this case is we know that this distance here, well, we know that you should actually draw this to scale, like nominal scale. We know that this is 610, and therefore we know the thickness of the flange, so we can find that out. And you should put this right in the middle between the top and the bottom flange, okay? That's where you should center that so that it's as close as possible to the center, the shear center of the beam, so it can minimize the effects. And that's it, guys. So there is a detail that we just calculated for ourselves, where we end up getting 390 as opposed to 230. So she might have calculated this with the threads being unintercepted. I don't know what kind of V4 she had here. I don't remember that, okay? But there you go. So that's the detail that we just finished doing today. And on the other page is the detail for the HSA. So the only thing that's left for you to calculate is to make sure the size of the plate that you need. And let's see what she used for the plate. You might as well use that as a trial section also. She made the gusset plate 8 millimeters. Well, you can try an 8 millimeter plate. I would try a 6 millimeter plate. I think that would work. I wouldn't even go to 8. There you go. Yeah. You see, she didn't dimension where her holes were, so I probably penalized her for that. Guys, these drawings, they're just one student handing in her drawings, and then I went and I made corrections. So 17.5. See, and I probably penalized her for this because she put a 17.5 millimeter plate. There's no such thing as a 17.5 millimeter plate. It's either 18 or 20. Use a 20 millimeter plate for the exterior columns. And then on top of that, okay, this here, keep in mind that although we don't get into it, okay, if this is 310 here, right, that means that her foundation wall would have to be 12 inches thick, okay, if she wants to be able to use this detail. If you don't want to, I just want to show you something here on this detail. Okay, you can put the anchor bolts on the inside here. You don't have to be on the outside. Oh no, wait. Yeah, they do have to be on the outside. Well, yeah, they have to be on the outside. Sorry, they have to be on the outside because this one has the bending one. Sorry, so that's correct. Not a problem. So guys, this is pretty much it. And then next week, what we're going to be doing, just to give you a heads up, what's going to happen is that we're going to learn how to calculate those double angle connections. That's going to be the lecture, and that's going to be the last thing for you guys to calculate. And after that, it's just finalizing your calculations, finalizing your drawings, and the project's pretty well completed. Is there any question, guys? Now's the time to ask. If there's anything on the question of the drawings, now's the time to ask. Just tell me what you want me to go over. I know Subitan wanted me to go over the web quickly. I can do that now. If there's no other questions. Subitan, do you want me to do that now?
Oh, it's up to you.
No, I mean, listen, we have time, you know. I've already pulled out the PowerPoint, so it's not going to be a problem to show you what we have to do. I need you to give me some values, understand? So we're going to have to do this, and I don't have the values with me. So, but before I move to the web crippling, is there any questions on what we did today? Wow. Okay, in that case, I'll stop sharing this.
Wait, 1 second. You know what we designed for, like, the VR that we designed for the 3.2 millimeter
Well, no, for 3
for the
millimeter.
HSS? Yeah.
Yeah, well, no, we calculated VR for a 3 millimeter weld.
Yeah, that's it. And we had a 27 millimeters the length for the weld, right?
27, right?
Yes, that's the end of the calculations, or we also have to do all those calculations for like the
Well, then you
shear.
have the other calculations that I gave you in that sample sheet that I sent everybody. You have to calculate the thickness of the plate required. And I tell you,
Okay, that's for the thickness that the
yeah,
sheet
exactly.
you
And,
gave us.
when I'm
Okay.
telling you, Vincent, try a 6 millimeter plate. It might most likely work. Understand?
Okay, thank you.
So start with a 6 millimeter plate. You've got all the geometry now, right? I gave you all the distances, right? Like,
Yeah.
let me just so we're all on the same page, let me just share this screen here, okay? So that we're all on the same page, so you guys know where you're going with this, okay? So right now, what we've established is this, okay? Here's our HSS that's going to be going up. Okay, that's our HSS. And now we are going to have, that's our plate that we are putting into our HSS, right? So far, so good. And what we've established so far is, okay, that we need to provide here only 27 millimeters of weld, but we said that good practice should be at least 1.5 inches, so make this 40. Okay, so that's 40, that's going to be 40 there. Then, so that's the weld there. Then we said we need 1 bolt, and it's good practice to have a minimum of 2 bolts, and we said we're going to be putting them side by side here, right? And of course, the good practice is that from here to here to here, we should have at least 35 and 35. So far, so good. So 35 plus 35 plus 40, now I've already established what the length of this plate here is. So that's 70 plus 40, this is going to be 110. So far, so good, right? Now we know we want to keep here an edge distance of 35. We know we want to keep here an edge distance of 35. And we want to keep here a distance of about 80. So that's 70, so this one here happens to be 150. Okay, and we know that this here is what? 114. So therefore, this leaves here 150 minus 114 divided by 2. So this leaves me about 18 millimeters here. And so therefore, I have ample space here to put this weld in here and the weld in there. And there's your geometry for your plate. Okay? So when you're doing the calculations, you just take this geometry and you just check your TR values.
Perfect. Thank you.
So guys, so here in this case here, it's basically the good practice that established what's the length of my weld. It's a good practice that established, like, for example, what this is a good, like, I only needed 1 bolt to resist that force, but good practice says you should have a minimum of 2 bolts, so I'll put 2. And guys, if this thing is twice as resistant as it needs to be, who cares? As long as it's not less, that's all I care about, okay? And now, like I said, as a trial section, try a thickness here of 6 millimeters, and it should work. It should work. And if it doesn't work, well, then you move up to 8. But I believe that 6 should work. Okay, so what we'll do is we'll move on, Subitan, we'll move on to the web crippling. Okay, so stop sharing and now, Subitan, here is the formula for the web crippling, okay? Sounds good? Now, all I'm going to do now, we need to have a couple of, we need to have some information. So, let me just, okay. Now, there's 2 things that can happen. Okay, so what I need to know is what is the CF force that's going into the column. And that was, like Andrew said, it was about 800, and whatever you designed the column for, that's the CF force that's going across here, okay? In other words, if this was a wood class, this would be your QF value, okay? And these give you what we call the QR values, okay? But they're called BRs. Now, here, this is simply a reduction factor, which is 0.8. This is the thickness of the web. So therefore, you got to take the W 610 by 113. Okay, and and this is the one that's sitting on top of there. And you got to go find the W for, in other words, the web of that beam. Okay. N is the length that you have. So if you design your base plate here, okay, whatever you design your base plate at the bottom, I'll just show it to you here. This here is called a cap plate, and this here is called a base plate. So whatever size of base plate, and I think we did this morning with Andrew, you use the same end up here. In other words, you use the same cap plate, and that's what you use for your end value. Okay. T, of course, is the thickness of the flange of your beam, and Fy, of course, is 345 MPa because you're using American steel. So if this BR here exceeds the whatever it was, the CF that's going in of 880 something here, then this one's okay. And then there's where the web crimples as opposed to yielding, and therefore this is the equation that you use. So this is the same reduction factor. This is the same value, and of course E is here. So you just plug in the values. And if both BRs are greater than the CF value of 800, I don't know what the value is, but what was it? Andrew, are you still there? Or is he gone? Is Andrew gone?
Oh, for the CF, I have 864 kilometers.
Okay, so if the BR is greater than 864, okay, if this BR and this BR is greater than, then you don't need it. You don't need to stiffen your web. So we can, right, I'm going to clear the thing so it'll be a little bit easier for you. So write down the equations here. This is the first equation. This is the second equation. N, like I said, N is this value here. So that's going to be your N value. In other words, the length of your cap plate, which is the same width as your base plate. Okay, so that's your N value. Okay, N is the length of bearing. And of course, that's going to be, I forgot what we decided was going to be this morning. And then after that, the T is the thickness of the flange, W is the thickness of the web, and then the phi BI is 0.8. So write down both equations. Go find the values of WT, and of course the N is something that you have to work out because you have to work out the size of your base plate, and that's what you use for your N for the top. We evaluate both equations, both BRs, and if they're greater than your CF value, then there's no stiffness required for your web.
Sir?
Yes.
Do we have to do this for both the exterior column and the interior column?
No, because the exterior column, okay, you're talking about the one at the wing column?
Yeah.
No, because I'm pretty sure that the exterior column, the wing column, the load is so little, right? The exterior column. In theory, I would check it if I was doing a real project, but no, I want you to just do it for the interior column. If you can do it for the interior column, then if one day you happen to have another situation where you have, just do it for the interior. But in theory, if I was doing this for a project, I'd also check it for the exterior. Just do it for the interior. Because if you do it once for me, that's I think that you'll know what to do, and if ever you need to do it again, you'll know, at least you'll know where to start. How's that? But in theory, yes, we should also be doing it for the exterior column.
So the only thing we have left to do is to design the double angle connections, right?
That's it. That's it.
And then
guys.
we're done.
That's it. The calculations are done, and after that, it's just finalize the drawings and put everything nice and neat together in a nice little package and ship it off.
Great.
How does that sound?
That's perfect.
I don't know about you guys. Like as of the end of today, I'm starting to see the light at the end of the tunnel.
I'm still not, honestly.
Yeah. Well, I can appreciate what you're saying, Vincent, because you got more than just my subjects.
I feel you, Vincent.
Pardon?
Light's getting a little bit too bright too quickly.
All those projects.
The train's coming a little too fast? Is that it?
I'm just barreling through the tunnel right now.
That's exactly.
But if you guys remember way back when, I warned you that come the end of the semester, you guys are going to get into a big crunch, right? And I told you this way back when.
Little did we know it would be all online.
Well, even if it was online,
Really?
Kaylee, it would still be, I'm sorry to use the word, but there would be a lot of work to be done at this time of the year. You understand? So I can sympathize, guys, and that's why I'm trying to give you as much help as possible so that you guys don't stress over this too much. You understand?
Appreciate it. Thank you, sir.
Thanks, sir. We appreciate it.
Yeah, really.
So
I have
look,
another
look, guys,
question,
it's
maybe.
3:40 now. I can come back at 4 o'clock if anybody wants me to come back at 4 o'clock. If there's anything else you want me to go over with on your project, it's up to you.
I have something.
You have something? So
Yeah,
we'll do
it's actually for AutoCAD. I don't know
AutoCAD.
if maybe like,
Yeah, hold
'cause
on a
I don't know how
second.
to change the scale
Can I
for some
just
reason.
like, I'm gonna pause the recording, okay, just in case okay, so we're recording again, and then I gotta go back to the AutoCAD. Share, okay. Now, I don't know if you guys ever notice this, but whenever first of all, you've got to pick some kind of plotting device, okay? So now, guys, when you have to plot your drawings to PDF, you can plot them to Microsoft Print to PDF here, okay? That's number one. And then you also have this one here. This is the one I like to use, AutoCAD PDF General. There's a whole bunch of PDF here. So you can use Microsoft PDF, whatever, okay? So let's say we were doing this to a PDF drawing like this, okay? Then the next thing you need to do is find your piece of paper. So in other words, now this is a full bleed. In other words, they're going to stretch right to the limits of the paper. And if you don't want a full bleed, then you take just a regular 8.5 by 11. But I'm just going to leave it here for now. It won't matter. Okay, full bleed, 11 by 17. Now, what I want you to notice that if I hover over here, over that little screen, you see the paper size? Everybody sees that? 11 by 17. But right underneath it is the printable area. In other words, that's what the program is going to be using in order to establish, okay, the area of the paper it's going to use to put your drawing on. So the printable area right now is 10.94 inches by 16.94 inches. Now, if I don't want to have it in inches, right, then, sorry, all I got to do here is change this to millimeters, okay, and I'm going to have it in millimeters. So my printable area is 277 millimeters in one direction and 430 in the other direction. Everybody sees that? So that's what will eventually be used to print my drawing. So that means that if I want to draw at a 1 to 200 scale, that means that the 277 gets multiplied by 200 and the 430 gets multiplied by 200. And that should be what we call the limits of my drawing. So if I take 430 times 230, I'm sorry, by 200. So if I take like that's 432, I take 430 by 200. So one limit I'm going to have is 86,000. That's going to be in the x direction. And if I take the other one, which was 277, so 55,400 in the y direction. So that's the limit of my drawing. So that's okay. Now, sorry, I want to cancel. Okay. Now, if you notice here, if I put a distance here, okay, from here to here, okay, you'll notice that the x direction is 82,000 and the y is 53,000. So I know that when I get to a ledger or 11 by 17, that will fit on my paper because I set the limits to that.
Oh, okay. That's
You
how
follow?
you do it. Oh, okay.
Because this way, and I know that once I put this border here, Vincent, right? Once I put this border in here, I know that once I click from there to there and I send it to my paper, it's going to fit at a scale of 1 to 200 because I am limiting my virtual space with my purple border.
Oh, okay. That's what I didn't get. So you can't actually like change like the scale like when you're
Yeah, you
bottom
can.
is.
All you got to do now is like, for example, I'll do it here. Okay, so now this is good for 1 to 200. So you take that concept and you apply it to what do you want to do your drawing with? Like in other words,
1 to 10.
huh?
Like, cause for the other two drawings, it's 1 to 10. So like, can you take this like the drawing you have right now and put it to 1 to 10?
Yeah, we can do that. Okay, so in other words, we can do that. In other words, what I'll do is I'll just say copy. Okay, so I'm gonna oops, I should. Sorry about that. Okay, copy. I'll copy the whole thing. And this is what you should be doing. Okay, from here, and you just move it over here. Okay. Now, in other words, now what you're saying is that you want your scale to go from 1 to 200, right?
Mm-hmm.
Down to 1 to 10. Is that it?
Yep.
You follow? Okay. So that means now that for every 1 millimeter of paper space, I'll only be putting 10 millimeters of what I'm actually drawing.
Mm-hmm.
You agree?
I agree.
So if I use the scale command, okay, I use the scale command, and oops, sorry. If I take the scale command, okay, and I take that as my base point. So what would be the scale?
1 to 10.
What's 10 divided by 200?
0.05.
So, okay, so therefore, it's asking me for my specified scale factor, 0.05, right?
Mm-hmm.
So now when I draw in here, I'm drawing 1 to 10.
Shit, okay. I
You
tried
follow?
you doing that and it never it never worked. 'Cause
Okay.
I think I was trying to put like 1 to 2, like 1 to 10. I didn't put
Okay,
like,
but now there's one more thing you have to modify.
makes
Okay,
sense.
so in other words, this is good for 1 to 10, but now all your annotation is 1 to 200. Okay, so you're gonna have to create more dimensioning for your 1 to 10 scale. Okay, and how you do that is very simple.
Okay.
What you do is you go to, okay, so, but you understand now, for example, if I take the concept that I did before, I have 277 multiplied by 10, so therefore my limit should be 2,700 in one direction, 4,300 in the other direction. You follow what I'm saying? Because that's my printable scale, right?
Sorry,
Now if I take, huh?
sorry to interrupt, but when you put in that 0.05 there, what did you write for this for the command to pop up? What did you write?
Well, I mean, I just scale my drawing. In other words, I use the scale command.
Okay, you just okay.
All I did is I did the scale command. In other words, I scaled this drawing down, okay, because it's going to need less space in order for me to put the information I need to put into it, okay?
Yeah.
And now, for example, if I had a printable scale of 277 multiplied by 10, now all I need is a limit of 2,770 by 4,300, understand? And if I measure this now, distance from there to there, that's what I have. I have 2,600 by 4,100, understand? So now I can fit this, and when I say, now, the other thing that you have to do is that when you're ready, when you draw in here, okay, you won't see it, because when you're drawing like here in AutoCAD, you like, okay?
So can you like basically finish your drawing on a 1 to 200 scale and then scale everything, like all the text and all the dimensions, back to 110?
If you want, yeah.
That would also work, right?
That would also
Instead of
work.
like always changing the scale for the text, always changing the scale for the dimensions.
Well, exactly. But the problem is that when you're drawing 1 to 200 to a scale of 1 to 10, you understand? You're gonna have to remember that all your dimensions, you have to multiply them by 200 to draw them, and then you can scale them down to 1 to 10.
Oh shit.
You see the drawback
that's
to
true.
that? That's the only drawback to what you're saying. Then you'd have to actually multiply everything by 200, and then when you scale it down, it will be to the right scale.
Okay.
But right now, this is the right scale. For your sheet, this is the right scale. You follow? Now, the only thing is that you're going to have to create a new dimension style. That's all you need to create, a new dimension style. So therefore, you're going to go to annotate, right?
Mm-hmm.
Okay, and you're going to go here, Okay. See, now this standard one here is what you're using for 1 to 200. You follow?
Yeah.
Okay. So what you're going to do is that you're going to create a new one. Okay. You're going to start with the standard. Okay. You're going to copy that. Start with this, and then here, what I tend to do is I tend to put 1 to 10. So I know which one I'm talking about. You follow? So this is a 1 to 10 scale. Whereas the other one is 1 to 200. I say continue. Okay? Now, here is where I come in and I modify the scale factor. Okay? So in other words, the primary units. Okay? This I don't have to modify. Fit. Okay? The overall scale factor was 4,000, right? I'm using that. What's 4,000?
Divided by what? 200?
Divided by 200.
20.
Pardon?
20.
Yeah, but then you have to multiply it by 10. So it's 200, right?
Yep.
Okay. Once I change the overall scale factor, okay? Now, if I make this current and press OK, okay? When I come in here, I hope this works, okay? And I do a linear dimension from there. You see how nice it is? It's to the right scale.
Yeah.
You follow? So that's all you have
It's
to
now like
modify.
80 millimeters and stuff. You can just put directly.
Directly, and then all you got to make sure that when you're on this drawing, you just go and change it to that dimension style. Understand? So you pop this up. Now, if you haven't do another drawing 1 to 50, then you just keep going. Understand? So now you can draw 1 to 10, and you can dimension 1 to 10.
Okay. Where did you click again for that dimension style manager?
Well, that's right here. It's under annotate.
Yeah.
It's under annotate, and then you flip out the dimension style here. Understand? So there was only one before. So I say create a new one. Like if I want to create one for 1 to 50, I would create a new one, and I would go in there and modify just the overall scale factor. So all my arrowhead size, all my text size, everything stays the same.
Okay.
Isn't that nice?
Perfect. That's perfect.
Isn't that easy?
So for this, sir, yeah, when you go to print,
Then
you
you
just
you send it.
it's the purple border that you
Right
use.
now, exactly. Now, Kaylee, just to show you, let's say I'm printing this drawing here. Okay, I would do plot, right? Okay, I don't have that here. Okay, so now I'm going to say PDF. Okay, PDF. Let's go to PDF. PDF general. Where's my PDF? I like using this one. PDF general. That's going to be my sheet size, right? I'm going to plot a window. Okay.
Yeah.
I'm going to plot a window. So now I'm going to plot the window from there to there. Then I'm going to center it, and I'm going to say my scale now is 1 to 10. Right? I'm going to make sure that's monochrome. That's okay. I'm going to ask for preview. Look at that. It fits. On the 11 by 17.
Interesting.
Very good.
What do you mean very good? This is basic.
I'm impressed. No, I'm kidding.
Oh, you're
Yeah,
impressed?
that's not how we learned it, sir. It was a whole different.
You're impressed on my skills with AutoCAD?
No, it was just always a hassle when we had to print stuff. So
Always.
this actually made it so simple.
Isn't this simple?
Yeah.
And guys, unfortunately, they took the drawing away from me last year. Okay?
You shouldn't, sir.
I got it back for next year. So, I mean, I'm the one that's got the most experience in drawing in the department, and they don't give me the drawing course. Go figure.
Who did they give it to?
Carmen, you did both drawing courses last year.
Yeah, I had a. No, never mind. I didn't have a course with them.
Anyway, so see how simple that is? And you do the same thing for wood. So, for example, you have 1 in 50, and then when you want to do your drawing, you do the same concept. And if you don't remember, I'll do it again next week. Understand when we're doing the drawings again.
Okay, well, thanks a lot. That was really helpful. I
It's
can actually
simple,
do my drawings now.
and you like the way that the arrowheads and the scale and the text have all been adjusted by changing that overall scale factor.
Yep.
Okay.
For
just remember,
steel,
pardon?
for wood, you didn't put like the dimensions for how much, like the text height that you wanted us to use. Can we just take one that like that?
Okay.
Just,
well, look.
good?
it's very simple. Like I'll tell you right now. Okay, first of all, remind me what scale the drawings are.
For wood?
Yeah, what's the scale of the drawing? If you tell me the scale of the drawing, I'll tell you the text.
I have to open it. Give me a sec.
So, because I don't remember it either. So, is it 1 to quarter inch is equal to a foot? An eighth of an inch is equal?
Yeah, it's a quarter inch to a foot.
Okay, so the maximum text size should be 6 inches maximum. Okay.
Okay, you already said it. Never mind. You already said it. You just didn't like put like a. Yeah, it's all good. Never mind.
It's good.
Oh, sorry, can you repeat it? I don't have it.
It was
Okay,
already,
so in
like,
other words,
said.
if you're drawing at a quarter of an inch scale, the maximum height of your text should be 6 inches.
Even for
Okay.
the for like
Okay.
the 1, 2, 3, 4, 5, like the center lines.
Oh, and guys, when you do
That's
your
small.
bubbles, okay, look, it's very simple. I'll explain this once, okay, and this way you guys can have this. Okay, so let me exit this.
It was too small for the bubbles. Like you couldn't
No,
see
no,
it basically.
Matt, look, let me explain to you bubbles once and for all, so this way you'll remember for the rest of your life. Okay?
Yep.
I'm gonna cancel this. Now, I'm gonna explain it here let me explain something to you, okay? I'm gonna annotate. I'm gonna annotate right here on my drawing. Okay. Bubbles are very simple, okay? A bubble should not take more than 3/8 of an inch of your paper scale. Do you understand?
Okay.
That's an imperial. And when you're doing a metric, to make it simple, it should not take more than 10 millimeters. You follow? That should be after I printed my drawing on my paper, that circle should not measure more than 10 millimeters or 3/8 of an inch. That's what I mean by on the paper. Okay. So far, so good?
Yep.
Okay.
Yeah.
Now, if I have a scale of 1 to 50, right? That means for every millimeter of paper, I got 50 millimeters on my drawing. So for a scale of 1 to 50, what should be the diameter of my bubble?
500.
500.
So it's the same thing for what's the scale? 1 to 4 is equal to.
Okay, so in other words, if I'm doing this in metric, right? The diameter here should, if I put a 500 millimeter diameter, if I'm plotting at 1 to 50, the final size on the paper will be 10 millimeters, and that should be the size of a bubble. Okay, so remember that. What you need to remember is 10 millimeters paper scale for metric, 3/8 for imperial. Now, when you're actually drawing at a quarter of an inch is equal to 1 foot, right? Right? You understand? Well, a quarter of an inch is equal to 1 foot. That means for every 1/4 of an inch, right? I'm taking up 1 foot of drawing space, right? Now, if I want 3/8, what would be the diameter of the bubble that I need to end up with a 3/8 inch diameter on my paper scale? Just do the proportions.
I have no idea.
1 foot, a foot and a half, it's got to be an 18-inch diameter. If I'm drawing 1/4 of an inch is equal to 1 foot, Mason, right? That means for 1 foot, I've taken up a quarter of an inch of paper. You understand? If I want to take up 3/8 of an inch of paper, and that's going to be the diameter of my, so how much more is this? That's 12 inches, and that's 6 inches. So therefore, the diameter of my bubble has to be 1.5 feet.
Okay. Because I did mine 2.4.
And if you hand that in,
It's way too big.
you're going to lose marks.
Okay.
So in other words, for your quarter of an inch, you do, like in other words, just remember what your paper scale is for your bubbles, and then you do the math. That's how I remember.
Okay, so that's why, like,
That's why they look big, right?
they looked big, yeah.
Yeah, and don't forget, when you're doing the drawing command, okay, just I see a lot of people make this mistake. They always use radius instead of diameter, okay, and that's another big mistake, okay? In other words, when I go to home, okay, home, and when I do the radius command here, okay, people always tend to make this mistake in taking this one, and then they put 1.5 feet, so they end up with a 3-foot diameter. It's twice the size that they need, okay? Now, here, this is what you want. Like, in other words, if I was doing it 1/4 inch, I say scale, right? And okay, this here is an imperial, right? As a matter of fact, if I come here, okay, this is 1 to 10. Do you agree we made this drawing 1 to 10, Basin? Okay, so if I go 1 to 10, and I happen to have 10 millimeters, that means that this diameter shouldn't be more than 100 millimeters. Agreed?
Yep.
Okay, so let me measure it. Guess what? It's 100 millimeters. Look at the bottom of the screen.
Yeah.
Isn't that nice?
Yep.
Do you guys know how to justify your text?
No.
You don't know how to justify your text, okay? So in other words, if I draw a circle here, okay, I'm gonna draw a circle, I don't care where it is, okay? I'm gonna draw a circle here. Here's my circle. And now if I want my text to be right in the center of my circle, right? I do dtext, right? That's text. I'm sorry, it's taking a while, okay? Now, before I do anything, if you look at the command bar, it says justify. I press a J, and these are all the justifications that you have to place your text. Left, center, right, middle, blah, blah, blah. So I want right in the middle of that circle, so I press middle. Then it tells me, give me the middle, okay? So, I didn't, okay, hold on a second, I gotta go back. I didn't press M. Okay, so let me do that again. I do dtext, then I say justify, and then I say middle. Then it tells me specify the middle point. I say I want it to be right there. Now 600, this would be too much. I should change the text size to, well, I should reduce this. Anyways, it's gonna be way too big. I should maybe make it 100. Well, wait, 600. Anyways, I'm gonna leave it at 600. It's gonna be way too big. 0, and now I can write something. Look, the text is way too big. But
How would you size the text without going into properties?
well, like in other words, what you do is simply, okay, this is why, guys, you know, you always have one of these. Believe it or not, even if you're drawing with Autodesk and AutoCAD, you still need one of these, okay? So, John Michael, this here, I'm drawing at a scale of 1 to 10. So I look at my scale, 1 to 10. Oh, here's my scale of 1 to 10. And I don't want my text to be any more than that much on my paper. So I can see right away at a scale of 1 to 10 how much it is. Oh, so that's going to be 50 millimeters. So therefore, I'll put my text height to 50. So that's how this helps you decide, if you can see it, that's how this helps you decide what you're going to be putting down for your text size.
All right.
Okay? So in other words, if I would have gone now, for example, dtext again, right? Justify. I put the middle, and now my, okay, specify middle point right there. Now I put down, I said this should be 50. And now I can put the letter A in there. Isn't that nice?
Okay.
Okay, so it's the scale here that tells me how big my text size is going to be. So that when I plot this at 1 to 10, it's going to be the right size. So guys, look, I'd be more than happy, like if you guys are improving, but like for me to do these drawings, believe it or not, like for me, these 4 drawings would be done in a day, you understand? But I've been doing AutoCAD since 1987. So a slight difference between my knowledge of AutoCAD and yours, but I can tell you that I try to teach AutoCAD so that you guys can be as efficient as possible, okay? And so, does that clear it up, Vincent, for you?
Yep. Thanks a lot.
My pleasure. So just remember these two things, Vincent. 10 millimeters, 3/8 of an inch. That's the diameter of your paper scale. From
Yeah, I
there,
just
you can
changed
just
it.
work out the math.
I just changed it on my drawing.
Sorry?
I just changed it on my drawing.
Okay. And you know, to change it on your drawing, you had a diameter of how much?
Before I changed it, I had a diameter of 2.5 feet. Now I have a diameter of 1.5 feet, like you.
I hope you use the scale command to change it and not redraw it.
Yeah, I just redrew it and just redrew one that I copied for all the other ones.
Okay, because you could have, okay, all I'm saying is that you could use the scale command and you would have the same result.
Yeah.
Okay, anyways, that's the problem with AutoCAD. There's 18 ways to pick your nose. You always try to find the fastest way to do it.
Love AutoCAD. It's actually really fun. Like, I
Okay,
don't mind doing it. Like, there's some stuff that I hate doing, but it's not too bad.
Okay, so guys, any more questions that we can clarify at this point here? So there you go. And if you don't remember how to do this, I'll repeat it next week because I have AutoCAD on my desktop here. It's not a problem. And I hope today was helpful. So yeah, yes.
When you're drawing the welds, what line weight do you use?
Oh, that's already all set up for you. Like if you go to the Properties Manager, okay, you have nothing to worry about. When I set up the prototype drawing, as long as you're drawing in the right layer, then you're gonna have the right line width. So if you open up the Layers Manager here, okay, I'm sorry, Mike, okay, and if you look, I've already, like for example, if when you're doing your text, you do it on text layer, the line weight is already set for you here. Okay, so this is all set for you here. You don't have to worry about that. For example, your center lines, those have to be in the very background of your drawing. So I have a very small line weight. So this, all of your line weights have already been set up for you here. As long, and what I do, Jared, you're the one that asked me a question?
Yeah.
Like, when I do an AutoCAD drawing, believe it or not, I start with objects and I draw all my objects. And I do it in one color, in a sense, so I know that I'm on that layer. Then when I move to another thing on the drawing, for example, if I move to text, then I change my layer to text and I do all my text. Then if I do all my dimensioning, I change and I do all my dimensioning, understand? So this way, by making sure that I'm doing everything on the right layer, when I go to plot, right here, this is gonna make sure that you're doing everything according to the right line widths.
Okay, yeah, thanks.
So that's all set up for you right there, okay? So don't worry about it, just worry about making, like for example, you'll notice here, I don't know if I have it here. Yeah, you see here, as a matter of fact, I've created two layers, one for columns and one for objects, okay? Because when you're doing a structural steel drawing, the columns should be a little heavier than your object lines. So what I did for you is that when you do your columns, make sure you do them on columns, and they're going to be drawn at 0.25 millimeters line thickness, and then when you do your objects, it's going to be at 0.20. So there's going to be a slight difference in the line weight between the columns, and that's going to make your drawing look much nicer. So make sure you start your columns like, so when you're doing your roof plan, put all your columns on your column layer, then change layers, and then start drawing all your objects on your object layer. And so, okay. So there you go. And like you notice, guys, I don't play more than three or four line weights. In my days, what we used to do, since we had line weights, and at the same time, we would even play with the ink that we used to use to plot, because if we use a yellow ink, it would be a very dark line. If we use a blue ink, we get a very light line. So we not only would we plot with different line weights, but we'd also try to plot with different line intensities. But this was way back when we have pen plotters, understand? So this is all old school, not even around anymore. Okay, so that's it. Hey, Vincent, look how small that drawing is compared to that one. Look at this one. It looks like a junior next to this guy. But when it comes to the paper scale, they're one and the same. Okay, so any more questions, guys, that I can answer? Because I'd be more than happy to go ahead and do it. I guess, is that it? Do you guys want to call it a day? Can I just end the screen and then, oh, I've lost quite a few people. Okay, so I guess Subitan is gone. So I guess I'm going to stop the recording now. Pause, stop.